Today, we're taking you inside the factories where fiber optic cables are manufactured and following their incredible journey all the way to the bottom of the world's oceans. Chapter 1: The Digital World's Nervous System. Fiber optic cables have become the backbone of modern civilization. They stretch beneath our cities, run underneath highways, cross mountains, travel through deserts, and extend for thousands of kilometers beneath the oceans. Together, these underwater cables carry almost all international internet traffic, connecting data centers, financial institutions, cloud platforms, governments, and billions of connected devices around the world. As artificial intelligence, cloud computing, and high-speed communication continue expanding, the demand for optical fiber grows faster than ever before. Modern technology companies are investing billions of dollars to build larger fiber networks capable of handling enormous amounts of data. Behind every AI response, every cloud backup, every international video call, there is an invisible network of glass fibers transmitting light across continents. Chapter 2: Inside a Fiber Optic Cable. Although it appears to be just another communication cable, its internal structure is incredibly complex. At the very center lies an ultra-pure glass core in single-mode optical fiber. This core measures only around 8 to 10 micrometers in diameter. To understand how small that is, it is several times thinner than a human hair. This tiny core carries information as pulses of laser light. Surrounding it is another layer of glass known as the cladding. Its slightly lower refractive index continuously reflects light back into the core, allowing signals to travel hundreds of kilometers with minimal loss. The delicate glass section is then protected by two polymer coating layers that shield it from moisture, scratches, and microscopic damage. Multiple fibers are grouped together inside protective buffer tubes filled with water-blocking materials. These tubes are wrapped around a central strength member before additional reinforcing materials like aramid yarn, fiberglass rods, or steel wires are added. Finally, everything is enclosed inside a durable outer plastic jacket capable of surviving decades of service. Chapter 3: From Sand to Ultra-Pure Glass. The manufacturing process begins far away from the factory, deep inside massive quartz sand mines. Large excavators remove thousands of tons of silica-rich sand every day. This raw material is transported into industrial processing facilities where it begins an extensive purification journey. The sand first passes through screening systems that remove stones and larger particles. It is then washed repeatedly to eliminate clay, dust, and unwanted minerals. Even after several cleaning stages, the material is still not pure enough for optical fiber. Factories must remove almost every trace of iron, moisture, and chemical contamination. Only extremely pure silica is selected. Out of hundreds of tons of raw sand entering the plant, only a small portion eventually becomes optical-grade glass. This remarkable level of purity allows light to travel enormous distances with almost no signal loss. Chapter 4: Manufacturing the Glass Preform. Now, the factory begins producing the heart of every optical fiber, the glass preform. A hollow silica tube is mounted onto a rotating lathe. Specialized gases containing ultra-pure silicon compounds are introduced into the tube. At the same time, a flame reaching nearly 3,600 degrees Fahrenheit travels slowly across its surface. Inside the tube, chemical reactions create microscopic layers of glass. Each layer is almost invisible, but after hundreds of repeated passes over many hours, these tiny layers gradually build into a solid structure. Engineers continuously adjust the chemical composition throughout the process. The outer layers become the cladding. The center becomes the optical core. Eventually, the hollow tube collapses into one perfectly solid glass rod. Although it measures several centimeters in diameter, the exact light path of the future optical fiber has already been engineered inside it. Chapter 5: Drawing the Optical Fiber. The finished preform is transported to one of the tallest machines inside the factory, the fiber drawing tower. The glass rod is suspended at the very top before being lowered into another furnace operating at nearly 3,600 degrees Fahrenheit. Its lower end begins to soften. Gravity stretches the molten glass downward. Precision pulling wheels gradually transform the thick glass rod into an incredibly thin fiber, measuring only 125 micrometers. The fiber now travels through the tower at speeds exceeding 3,000 feet every minute. At such incredible speed, maintaining a constant diameter becomes extremely challenging. Laser measuring systems continuously monitor the fiber. If it becomes even slightly thicker, the drawing speed automatically increases. If it becomes thinner, the system instantly slows down. This entire operation is controlled automatically with extraordinary precision. Chapter 6: Protective Coating and Inspection. Freshly drawn optical fiber is surprisingly fragile. Immediately after leaving the furnace, it enters an automatic coating system. Dual polymer layers surround the glass before ultraviolet lamps instantly harden the protective coating. The fiber then moves through advanced inspection equipment, high-speed cameras, laser scanners, diameter sensors, roundness measurement systems. Every millimeter is inspected. Even the smallest imperfection can lead to rejection. Chapter 7. Proof Testing and Color Identification. Each optical fiber must now prove its strength. The production line applies approximately 100,000 pounds per square inch of controlled tension. Any microscopic crack immediately causes failure. Defective sections are automatically removed before the fiber continues. After passing inspection, every fiber receives its own unique color. Extremely thin UV-cured coatings allow technicians to identify individual fibers during installation and maintenance. The colored fibers are then grouped into ribbons or buffer tubes, preparing them for cable assembly. Chapter 8. Building the complete cable. Now the optical fibers become a real communication cable. Buffer tubes enter a stranding machine where they wrap helically around a central strength member. This loose tube structure protects delicate glass fibers from pulling forces and thermal expansion. Water-blocking gels and swellable tapes prevent moisture from entering the cable. Depending on its intended use, additional reinforcing materials such as fiberglass rods, aramid yarn, or steel wires are added. The complete assembly enters an extrusion machine. Molten polymer surrounds the entire structure, creating a durable outer jacket. The cable then passes through a long cooling system where the jacket rapidly hardens. Some modern cables can contain more than 800 optical fibers inside a diameter smaller than 1 inch. Chapter 9. Mechanical Testing. Before leaving the factory, every cable must survive demanding quality tests. Powerful testing machines stretch the cable under hundreds of pounds of force. It is bent, twisted, crushed, struck, and compressed repeatedly throughout every test. Laser equipment continuously monitors signal transmission. If even the slightest signal loss occurs, the cable fails inspection. Engineers also perform water blocking tests by exposing the cable to water pressure for extended periods. Only cables meeting every mechanical and optical requirement receive final approval. Chapter 10. Preparing for shipment. Approved cables are wound onto enormous steel or wooden reels. Each drum may contain several miles of continuous cable. Both cable ends are carefully sealed to prevent moisture contamination. Detailed labels record every technical specification before shipment. The reels are securely fastened for transportation because even a single heavy impact can damage the delicate glass hidden inside. Chapter 11. Laying fiber across the ocean. Manufacturing is only half the story. To connect continents, fiber optic cables must cross the world's oceans. Near coastlines, cables receive multiple layers of heavy steel armor for protection against anchors and fishing equipment. Special survey ships first map the seabed to determine the safest installation route. The cable is carefully coiled inside enormous onboard storage tanks. As the vessel moves forward, sophisticated computer systems precisely control the cable's tension and deployment speed. In shallow water, underwater plows bury the cable beneath the seabed. In the deepest parts of the ocean, where human activity is minimal, the cable simply rests directly on the ocean floor. Even the smallest installation mistake can damage thousands of kilometers of communication infrastructure.